All right, so up till now in this gases unit, we've been dealing with ideal gases, gases that obeyed kinetic molecular theory. But we know that in the real world, there's no such thing as an ideal gas. Ideal gases don't exist in the real world because an ideal gas, the particles have no volume, according to kinetic molecular theory. But in the real world, molecules and atoms, although they're small, they definitely have volume. We also said that in ideal gases, particles collide elastically. They don't lose any energy when they collide. But in the real world, every collision between particles loses a tiny bit of energy. So there's no such thing in the real world as ideal gases. Instead, we have real gases, which raises the question, well, then why would we study something which is fictional? Why study ideal gases if they don't match what we have in the real world? And that's what we're going to talk about here. Okay, so real gases. Take a look. You want to sketch what you see here on the left-hand side. This is a graph. You don't have to sketch it super carefully, but you want to sketch it roughly. So it's a graph of PV over, now this one says PV over nRT, that's fine, versus pressure. Now think about that y-axis for a minute. This is important. PV divided by nRT. The ideal gas law said that PV was equal to nRT. So if you were to divide both sides by nRT, you'd get PV divided by nRT equals 1. If you were an ideal gas, PV divided by nRT has to give you 1. So now when you look at this graph, at the value for 1 on the y-axis, there's a dotted line. And that dotted line is labeled ideal gas. Okay, so if you were an ideal gas, no matter what the pressure was, okay, look at that x-axis. This is crazy. Those are atmospheres. 0, 200, 400, 600, look at that. 800, 1,000 atmospheres. Can you imagine how big that pressure is? Normal pressure is 1 atmosphere, right? So these pressures are tremendously large pressures. But if you were ideal, if a gas was ideal, no matter what the pressure was, if you divide PV by nRT, you have to get 1. Now look at some of these actual gases, real gases. And you'll notice whether you're hydrogen, nitrogen, oxygen, ethene, C2H4, or carbon dioxide, no matter which real gas we pick, none of them look like they behave at all like an ideal gas. Like look at carbon dioxide on here. Carbon dioxide's behavior falls way down and then goes way up like that. So none of these gases look like they behave ideally at all. And that's kind of disturbing because we've been studying ideal gases. Well, if real gases don't behave at all like ideal gases, then we have a problem. But the key was the pressure axis. These pressures are huge. These pressures are nothing like the pressures that we normally encounter. So now look at the right-hand graph. The right-hand graph is still PV over nRT, but notice you've zoomed way in. Instead of 0 up to 2.5, which was the original y-axis, now we have 0.92 up to 1.02. So that's very close to 1. And now look at the pressure axis. Instead of 0 to 1,000 atmospheres, this is 0 to 10 atmospheres. Well, 10 atmospheres is still 10 times greater pressure than the normal pressure, but it's not hugely beyond what is normal pressure. And now look at these same gases. Carbon dioxide still looks kind of crazy, but even carbon dioxide, when you're at 10 atmospheres pressure, PV over nRT, instead of equaling 1, it's 0.92. So it's pretty close to 1, even though it's not exactly 1. Look at the other gases. Even at 10 atmospheres pressure, when you do PV divided by nRT, you don't get 1, but you get something very close to 1. So here's the takeaway message from these two graphs. Real gases, when they're at very high pressures, like we saw in the first graph, they deviate from ideal behavior. Real gases show large deviation from ideal behavior when they're under very high pressure. But if the real gases are under low pressures, if they're under pressures that are at or close to standard pressure, then real gases behave pretty close to what an ideal gas predicted. So the ideal gas equations we've been using successfully describe real gases under low conditions of pressure. That's the takeaway message from these two graphs. Okay? At low pressures, real gases behave ideally, but under high pressures, real gases do not behave ideally. They deviate. Question is why? Why do they deviate from ideal behavior at really high pressures? That's what we're going to take a look at. Any questions about that, folks? Anybody need more time to copy that? All right. So this graph is showing us the same kind of thing, but this time it's got a little bit of a difference. Look at these three curves on this graph. It's still PV over nRT. It's still pressure, but again, those huge pressures from 0 to 1,000 atmospheres. But now these curves are not different gases. These curves are different temperatures. Okay? The purple curve is 173 Kelvin, a pretty low temperature. The red curve is 873 Kelvin. And what do you notice about the effect of temperature on the behavior of real gases? If the dotted line is 1 on the y-axis, so that's your ideal behavior. You guys can no longer see this, right? Let me try sharing that again. Okay, so if the dotted line is ideal behavior, where PV over nRT gives you 1, what can you say about the effect of temperature on the behavior of real gases? When the temperature is low versus high, what's your conclusion from that? Well, at high temperatures, this red curve, doesn't it look like it's closer to ideal behavior than it is at low temperatures? So the takeaway message from this is that at high temperatures, gases are more, real gases behave more like ideal gases. At low temperatures, they deviate. Okay? So when do real gases deviate from ideal behavior? What are the two where do they deviate? Well, for pressures, it would be under high pressure. They deviate. But for temperature, it would be under low temperatures. You could reverse the question and say, when do real gases behave most ideally? Well, that would be under low pressures and high temperatures. Okay, so that's a very important takeaway from this discussion. But we still have to answer the question, why is this? Why do gases behave less ideally when they're at high pressure and under low temperatures? What's the problem with high pressure and low temperature? Well, in this picture on the left, you see a container full of gas, and it's under low pressure conditions. On the right-hand side, the container is full of gas under high pressure conditions, so the volume is lower. Can you see something in those two pictures that relates back to the assumptions we made in kinetic theory?
Yeah. So the volume, like the percentage of volume that the low pressure molecules take up out of the entire volume of the container is a lot lower. But because there's less total volume in the container for the high pressure picture, the volume of the molecules themselves have a higher.
Percentage,
They take
right?
up more, yeah, higher percentage
Okay.
volume.
So what you're getting at is one of the assumptions we made in kinetic molecular theory. We assumed, so KMT assumption, we assumed that gas particles have no volume. So their volumes are negligible, each particle. But as was just pointed out, if you have high pressure, then you have lots and lots of particles squeezed into that small volume. Then even if the particles have a tiny volume each, when you have so many particles in such a small volume to create a high pressure, the particle volume becomes significant. Whereas in the first picture, when the particles are spread out far apart from each other, there the particle volumes themselves, each little particle's volume, is kind of insignificant compared to the volume of the entire container. So at high pressures, the assumption that the particles have no volume becomes a problem. Does that make sense?
Yeah.
There was another assumption we made in kinetic theory besides the elastic collision one, which we already talked about. Do you remember also discussing that in an ideal gas, there are no what? There are no
Intermolecular forces.
intermolecular forces. And remember what that means. There are no IMFs. What are intermolecular forces? We talked about how a particle, I'm going to draw a big particle. Here's a big particle. One side of this particle, for various reasons, might have a partially negative charge to it, while the other side of that particle might have a partially positive charge to it. We would say that that particle is polar because it has a positive and a negative side. If there's a neighboring, whoops, I just moved my picture. If there's a neighboring particle, another particle that's close by, that has, say, the same partial negative and partial positive, what's going to happen between these two particles right now, the way I've drawn them?
Repel each other.
They'll repel.
Right, the two negative sides are close to each other. So there's going to be a repulsive force between them. That repulsive force is an intermolecular force. Okay. On the other hand, if the positive side was closer to the negative side of the neighboring molecule, there'd be an attractive intermolecular force. So these little forces are always existing between particles. So what's the problem if you have high pressure versus low pressure?
They're more likely to come in like close quarters with each other, meaning there are intermolecular forces.
Yeah, like let me just be clear. There are intermolecular forces in both of these pictures, but the forces would be much stronger when the particles are closer together, right? If you have a negative and a positive object and they're very far from each other, well, they don't really repel each other very much, or sorry, attract each other very much. But if you bring the negative and positive particle close to each other, then the attractive force gets much stronger. So under high pressure, the particles are brought close enough together that their intermolecular forces are no longer negligible. Please ask me if you need me to explain that again. So under high pressure situations, the particles are so close together that their volume becomes a significant part of the volume of the container. So any intermolecular forces between the particles are stronger when the particles are close together. So now I hope you understand why that high pressure, non-ideal behavior. What about low temperatures? What's the problem with low temperatures? This one you can discuss on different levels of complexity, but
Um,
what happens
the
to
particles
all
won't be moving.
gases? Sorry, what happens to all gases if you cool them down eventually?
They
They'll
stop
condense.
moving.
Their density increases.
Before you reach absolute zero, when they would stop moving. What
Their
happens to the
density decreases.
their what?
Their density decreases
No.
or increases. Sorry.
Okay, but
They become liquid.
there you go. If you cool them down, their kinetic energy drops. They move more slowly, and then eventually, as you keep cooling them down, what happens to those intermolecular forces? They become able to hold the particles together. When they can hold the particles together, you no longer have a gas. You have a
Liquid.
Liquid.
And then if you keep cooling them down, even in the liquid, the particles will slow down and eventually they become
Solid.
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 So under low pressure, low temperatures rather, the particles have less and less kinetic energy. So eventually their intermolecular forces can pull them together into a liquid state. And that creates problems, obviously, in terms of PV over nRT. You could also argue that under high temperatures, looking at it the other way around, under high temperatures, the particles have so much kinetic energy that they can easily overcome intermolecular forces, right?
Yeah.
All right, so hopefully you understand now when gases behave ideally and when they behave non-ideally, and why. Now, there is a mathematical equation. I want you to write this down. It's called the van der Waals equation. For a Dutch fellow, Johannes van der Waals, I think his name was. It looks kind of ugly, this equation, but does it look a little familiar? Does this equation look a little bit familiar?
Yeah, it's got P and V on the left side and nRT on the right side, and it's
Yeah.
just a little more complicated on the left.
So it's kind of like a bastardized version of the ideal gas law, isn't it? This thing on the left in brackets can be thought of as a pressure term being multiplied by a volume term. But instead of just P times V, it's P plus some kind of weird thing here, and V minus some kind of weird thing here. Now, I don't want to go into great depth because we're not going to actually do anything with this equation. We're not going to see any word problems where you have to use this equation. But I do want you to know that in this van der Waals equation for real gases, that's what it's for real gases, there are two new letters. There's this letter A and this letter B. Those are correction factors for pressure and volume. The A is a correction factor for pressure. The B is a correction factor for volume. And those are not constants across all gases. They're different for every gas because every gas, the particles themselves, have different volumes. So you need a different correction factor for volume for every different gas. Also, the different gases have different intermolecular forces. So you're going to need a different correction factor for their pressures. So what you get is a table. I'm going to go back to van der Waals if you didn't finish copying it. You get a table like this where you'd have real gases. And if you ever wanted to use the van der Waals equation to calculate things in the real world, you're not going to think of them as just ideal gases. you'd look up the values for A and B for whichever gas you were dealing with. And then you'd use those values for A and B in the van der Waals equation. So you would do exactly what we've been doing with ideal gas law, but you'd insert these correction factors if you were dealing with real gases. And when would it be most important to use this equation instead of the ideal gas law?
At
At really high
pressure.
Pressures and low temperatures.
and low temperatures. And when we say really high, again, we're talking about hundreds of atmospheres of pressure, right? Not just 5 or 6 or 7 atmospheres. At low pressures and moderate temperatures, the ideal gas law works fine. Okay, so we're never going to need this equation in a problem. But if I asked you in a multiple choice question or something, tell me what the letter A in the van der Waals equation is for, you'd have to tell me, well, it's a correction factor for pressure because of the intermolecular forces between particles. What is the letter B? Oh, it's a correction factor for volume because real gas particles actually have a volume. They're not just points in space. All right. So real gas behavior versus ideal gas behavior, and the van der Waals equation, which if you wanted to deal with real gases mathematically, it would replace the ideal gas law. Okay? But I hope you do understand the ideal gas law, despite its flaws with its assumptions, works pretty well under most conditions that we would ever need to deal with, which is why we use it. Okay? All right, I'm going to stop my recording. I think I stopped my